In this lecture, I would like to demonstrate that the concept of reversibility can be effectively being used to analyze heat engines and heat pumps. In this first example, we have a heat engine with working fluid running between two reservoirs. The high temperature reservoir is kept at 550 Celsius. The low temperature reservoir is kept at 300 K. If the working fluid absorbs 1 megawatts power and the working fluid performs 450 kilowatts of power, then we shall be able to analyze this heat engine in two aspects. Number one, we shall be able to answer the question about heat being rejected to the low temperature reservoir and estimate the thermal efficiency of this heat engine. In the second aspect, if we assume this heat engine is operated under idealized conditions similar to the Carnot cycle, then can we estimate efficiency, the work being performed, and the heat being rejected to the low temperature reservoir? In order to answer the question of the first area, the heat engine is assumed to be an irreversible heat engine, and the heat rejected to the environment can be estimated based on the first law. That means QL dot equal to QH dot minus W dot. Thermal efficiency can be estimated based on the definition of thermal efficiency. That is the ratio of the work rate divided by energy absorption rate at a high temperature reservoir. For the idealized situation, the engine runs like a Carnot cycle with the efficiency being expressed in this fashion. And that the ratio of two Q terms for a Carnot cycle can be expressed as a ratio of two temperature terms. And again, the Q and the W term can be estimated based on first law and the definition of the efficiency. The one thing that is very important to know, the result shows the efficiency of a reversible engine is much higher than the efficiency of a irreversible engine, while the work performed by a reversible engine is higher than a irreversible engine, 450. The heat rejected is lower than the heat being rejected by a non-ideal heat engine, because most of the energy will be used in performing work. We can analyze air conditioning in a similar way in the second example. To quickly review how an air conditioner works, the working fluid, working as a liquid, enters the house through an expansion valve. When the liquid expands, it evaporates. Evaporation absorbs certain energy from the house. Then the pump, a compressor, compress the vapor to liquid and then reject the heat to the house environment before it returns to the house. If the air conditioner is operated in the ideal condition, and if the house is kept at 24 degrees C and its environment is at 35 degrees C, if we further assume that the 4 kilowatts of energy is needed to maintain the house at 24 degrees C, then we are asked to estimate the work required for this compressor. To analyze this problem, we use the definition of COP. The efficiency of this air conditioner is defined as the low temperature absorbed, the Q absorbed at a low temperature divided by the work performed by the compressor. And this ratio, if the air conditioner is operated in the idealized condition, this ratio can be expressed as a simple function of temperatures. This was what discussed in the last session. So the work term can be estimated based on this portion of the equation if the COP is estimated. As a note, the COP estimate based on these temperatures is 27, but it is much higher than those of a practical air conditioner. It's operated in the condition COP equals around 5. Now let's talk about what is the source of irreversibility. When we discuss heat engine, we mentioned that the working fluid passes through the two reservoirs at T sub H and T sub L. But in reality, the working fluid, when it passes through the high temperature reservoir, it hardly reaches TH. There is a finite temperature difference between the working fluid and TH. And the working fluid temperature is designated by T sub high. And that causes the irreversible heat transfer. Similarly, when the working fluid rejects the residual heat to the environment, the temperature is noticeably higher than TL, and the working fluid temperature is designated by T sub low, which is another source of irreversible heat transfer. And for the heat pump, when we discuss heat pump, we assume the two reservoirs are at TH and the TL. But the temperature of the working fluid when it rejects the heat to the environment, the working fluid temperature has to be significantly higher than T sub H because heat tends to transfer from high temperature to low temperature. So the working fluid is actually at a higher temperature than T sub H. When it absorbs the heat inside a low temperature reservoir, the temperature of the working fluid has to be at a lower temperature than the house temperature, so that the heat can be transferred from high temperature to low temperature working fluid. These again are the two sources of irreversibility of the heat pump. Then we should be able to analyze this problem, assuming the same situation of the house we discussed in the last example. If the house is maintained at 24 degrees Celsius, the environment is at 35 degrees C. In order to maintain the house temperature and the steady state, we need to remove 4 kilowatts of energy from the house. Now, we are asked to analyze two non-ideal situations. Number one, if the COP is only a fraction of ideal situation, what will be the power required? Number two, if the thermostat is reduced from 24 to 20 degrees C for our comfort, what will be the new power requirement for this non-ideal air conditioner? Let's analyze the first part. We already know the COP, the actual COP for this non-ideal air conditioner is a fractional number of what we estimated before, which is 6. And then we can use the definition of COP to estimate the required work. And I'd like you to pay attention to this number. This required work is about 4 times of the work done in the last example. That means when the irreversibility causes our electrical bill to increase about 4 times. Next, if the thermostat temperature is reduced from 24 to 20 degrees C, what will affect the power requirement? We can start with the same definition of COP. And we already know this COP is, if we lower the thermostat temperature from 24 to 20, the new COP is only 4.34. Notice this is lower than what we just estimate. And then before we analyze the Q term, we have to realize if QL dot term is still the same as this given QL term, the answer is not. The reason is this. The QL term in these cases, in both cases, is maintained at a steady state, then this QL dot term is equivalent to the energy leak into the house from the roof, from around the wall of the house. So we can anticipate if the house is maintained 4 degrees lower, then the QL term will be higher because the driving force for the heat transfer will be higher, so the required heat removal rate will be higher than what we estimated before. So how do we handle this QL term? Remember when we discuss heat transfer, when we talk about heat transfer in the last chapter, heat transfer through the roof can be assumed to be proportional to the temperature difference. That is equivalent to say the heat leak into the house is proportional to the temperature difference between the environment and the house. C leak is a proportionality constant. Is this a constant? Yes, we can assume it's a constant for this simple example. If we assume this constant remain constant when we change the thermostat temperature, then when we change the temperature gradient, then we change the Q leak term. So let's analyze the first case as example. 4 kilowatts of power is needed for this for the first scenario where the house is maintained at 24 degrees C. Then we can use the first scenario to estimate the constant. Then if the constant is obtained, then we can estimate the QL dot term based on the constant. Once this QL dot term is estimated, we can estimate the work required for this compressor. Notice the final answer for this irreversible heat pump is 1.25 kilowatts, compared with what we obtained in the last example. The number is 0.667. This number doubles the number. That means our electrical bill doubles. This concludes this segment of my lecture.